All right, now we're going to get to the good stuff. Let's go ahead and start talking about the derivative. So pretty much half of calculus, right? Derivative. The other half is the antiderivative. So we're going to be doing a lot of stuff with derivatives, and then we're going to be going backwards and do what we call an antiderivative. So let's get into it. You saw in the previous section that we talked about the formula where we have the limit as h approaches 0 of f of a plus h minus f of a all over h, right? We used that formula to find the instantaneous rate of change. We took the 2 points, we found their slope, but then we squished those 2 points so close together we found the instantaneous rate of change. Well, now we're going to use that same idea to help us find the slope of a tangent line. Well, a tangent line is a line that only touches our function once at one point. 1 point here, 1 point here, 1 point here. And so if we want to find the slope of that tangent line, we need to find the slope if it only touches once. Well, normally when we find the slope, it has to be 2 points, right? It has to touch twice, a secant line. We can do our y2 minus y1 over x2 minus x1. But if we don't have 2 points and we only have 1 point, how can we still find the slope? Well, we can use our instantaneous rate of change, the slope at exactly 1 point instead of 2. So this formula will actually work for both things. We can use it to find the instantaneous rate of change, which is really the same thing as the slope of a tangent line, or the slope at exactly 1 point. So if we can find the equation, or we can find the equation of a tangent line if we can find its slope. Normally though, we need 2 points to find the slope. But if we can take the slope and move them, those 2 points and move them so close together so that h is 0, what we're really doing is finding the slope of the tangent line. So this formula not only works for instantaneous rate of change, but it also helps us find the slope of the tangent line. So this formula is very useful. Let's do an example. Example number 1 gives us a function f of x equals x squared plus 2. So I know it's going to be a parabola shifted up 2. The first part is asking us to find the slope and the equation of a secant line through the points where x equals -1 and x equals 2. So they kind of give you a graph down here. We have the point at x equals -1 and the point at x equals 2, and you might notice this green secant line that touches twice at 2 points. So we just have to find the equation of that line. Well, there's 2 things I need for an equation of a line. And I need my equation to probably be in slope-intercept form, y equals mx plus b. And in order to find an equation of a line, I need a slope and I need a point. Well, they actually don't give me either a slope or a point. They just give me 2 x values and an equation. But if I have 2 x values, x equals -1 and x equals 2, we should be able to plug those 2 values into my function or in my equation and get the y values that correspond, right? So we should be able to plug in -1 into my function and figure out what y is. And we should be able to plug in 2 and figure out what its y value is. I'm going to do that now. So I actually have a point at -1, 3 and 2, 6. And now that I have 2 points, we should be able to find the slope, or the average rate of change, right? My y2 minus y1 over x2 minus x1. So let's do that now. I ended up getting 1 for my slope. So that's halfway done. The other thing that I need, though, in order to come up with the equation of a line is a point. I have a slope, 1, but now I need a point. Well, we actually have 2 points, don't we? We have -1, 3 and 2, 6. You should be able to pick either of those points and use the slope of 1 to find the equation of your line. So let's pick one of the points. I'm just going to pick 2, 6 for this example, and the slope that we found of 1, and put those 2 things together to help us write the equation of a line. Hopefully, you've seen point-slope formula before. Y minus y1 equals m times x minus x1. As long as we have a slope, and as long as we have a point, we should be able to use this equation to find the equation of any line. So I'm going to use this equation. I'm going to plug in the x of my point, the y of my point, and my slope of 1. I'm going to distribute the 1 through. I'm going to add 6 to both sides, and I ended up getting the equation of this secant line as y equals x plus 4, which looks right. It crosses the y-axis at 4 and has a positive slope, so I can find the equation of any secant line. You've probably been doing this for a long time. But what happens if I change the question and I asked you to find the slope and the equation of a tangent line? And now I want the line that touches this parabola, the x squared plus 2 parabola, at exactly x equals -1. You notice this line right here just barely touches that parabola at one point at x equals -1. And I need to find the equation of this line. Well, if I'm finding the equation of a line, I need those same two things. I need a slope and I need a point. Well, I have a point. It touches at -1, 3, but I'm missing a slope. And I don't know how to find the slope if it only has one point. But we do. Remember, we have that instantaneous rate of change formula, the slope of a tangent line formula. We can take that -1 and then a point a little bit farther away, -1 plus h, and we can make h go to 0, so we're finding exactly the slope at x equals -1. So let's do that now. So I have the limit as h approaches 0 of f of -1 plus h minus f of -1 all over h. Now we just have to do some algebra. We have to take that -1 plus h and plug it into our function wherever we see an x. And we have to take the -1 and plug it into our function wherever we see an x. Remember, our function was the x squared plus 2. Here it is, x squared plus 2. So here we go. Maybe you should pause the video, get some extra practice on your own and make sure you're doing it right, and then come back and check your answers with mine. All right, I'm going to plug in a -1 plus h wherever I see an x. I already plugged in a -1 earlier and I got 3, so there's where 3 came in. And then don't forget you have a plus 2 from your equation. I'm going to do a little bit of algebra and FOIL that out and combine like terms. On my numerator, then I have a 1 minus 2h plus h squared minus 1 all over h. Remember, we're doing the limit as h approaches 0. Make sure that you continue writing that all the way through. The positive 1 and the -1 cancel. Everything without an h should. That means everything with an h can have that h GCF'd out. I can GCF out an h, and that leaves me with an h minus 2 all over h. The h in the numerator, the h in the denominator reduce. And so now I have the limit as h approaches 0 of h minus 2. I still have an average rate of change until I apply that limit, right? And so as we squish those points so close together where h, the distance between them is 0, and I plug in a 0, I ended up getting -2. That -2 really means that that's the slope of my tangent line at x equals -1. That's the slope of this pink line at exactly x equals -1. If you were to move this pink line, the slope would be a little bit different, even if you slightly moved it, wouldn't it? So this is exactly the point at this, exactly the slope at this point on this function, instantaneous rate of change. So now I have the slope of the tangent line, and don't I have a point, the exact point that it touches my parabola at -1, 3? And since I have a point and a slope, I should be able to put those things together and make an equation of a line. I have my y minus y1 equals m times x minus x1. You notice that my two negatives make a positive, and I can distribute the -2 through. I can go ahead and add 3 to both sides, and I end up getting y equals -2x plus 1. That is the equation of this tangent line. It makes sense. It touches at +1 on the y, and it looks like it has a -2 slope. So now I can find the slope of any secant line, and I can find the slope of any tangent line now, even if it only touches once, by using that same formula. So make sure you practice using that formula for instantaneous rate of change, or now slope of a tangent line, or even slope at only one point.